Hey guys, welcome to my channel iCode. I am Pallav and this is the second video of our series that is Mastering Concurrency in iOS. We are doing this series for understanding concurrency and everything around it in very detail, in very depth. In the first video of the series, we understood about concurrency, that what is concurrency, why is it, how is it achieved, what is the difference between concurrency and parallelism. We tried to understand the concepts like time slicing, context switching, how they help in achieving concurrency, and then we started with concurrency in iOS. We looked at how to create the thread manually, what are the recommended ways. We looked at GCD, what are dispatch queues, concurrent queues, serial queues, what are the differences between them. We had a very close look to understand that how serial is different from synchronous and concurrent is different from asynchronous. If you haven't watched the first part in which all of this was included, here's the link. Now in this second video today, we will dive even deeper in dispatch queues. We'll see that what is main queue, what are system provided global concurrent queues, how can we create custom queues. We'll look at the parameters which are used for creating the custom queues as in attributes, auto release frequency, target queues, and we'll try to understand them in very detail. We'll also try to understand quality of services and why it was introduced by Apple in the first place. What were the problems and how QoS helps in solving them. So let's get started. In the previous video, we saw that dispatch queue is an abstraction layer to which the tasks are submitted. GCD maintains a collection of these dispatch queues, and the work submitted to these queues is actually executed on a workers pool, on a pool of threads. Now let's see that what are the different types of these dispatch queues. So essentially there are three types of queues: main queue, global concurrent queues, and the custom queues. Now there are some similarities and some differences between three of them. So let's try to understand each one of them in detail. Main queue is one of the system created queues. It is serial in the nature of execution and it uses main thread. Now these 3 points are not very difficult to understand. We saw that serial queue executes one task at a time and main queue follows the same. It is one of the system created queues. We get a set of queues which are created by a system and main queue is one of them. So that is also fine. But the third point, that it uses main thread, this is something which differentiates main queue from the other queues. Main queue is the only queue available which uses the main thread. The access to main thread is not available to any other queue, be it system provided or be it user created. Also, UIKit is tied to main thread. So this creates a whole set of difference. We'll do a very detailed analysis of the fourth point, that why UIKit is tied to main thread. What can possibly happen if we try to create something like UIKit and try to tie it to any other background thread? Why is it necessary to update the UI on main thread only? Or why does UI freeze happens and the entire concept related to it? The things around that, for example, the main run loop, the view draw cycle, the refresh rate, everything else. We'll see everything in very detail, but that we'll do in the video in which we'll be covering the interview questions related to concurrency. This is because all of these points are very interrelated and it creates a very beautiful series of follow-up questions. So it's better to understand them in the form of questions and answers so that it not just clears the concept but will help you in answering the questions in interviews also. So for now, let's just understand that main queue is something provided by system. It is one of the system created queues. It is serial in nature of the execution. It uses main thread, and because UIKit is tied to main thread, we perform all the UI related operations on the main queue. Everything around this will be discussed later in this series. Now let's move to the second type of queues, that is global concurrent queues. Global concurrent queues are also system provided queues. They are created by system, and in that sense it is different from the user created queues. They are concurrent in nature of execution, unlike the serial queues or the main queue that we just saw. And the third point is that they do not use main thread. So there's a confusion, there's a very important concept which creates confusion, that can global concurrent queues use main thread in any of the possible ways. And one of the possible ways which creates a misconception is the user interactive quality of services. We'll see that what are quality of services, we'll see what is user interactive, what is the meaning of that. But for now, if you are having any doubt related to the understanding of concurrent queues, that can they use main thread or not, just make it clear that global concurrent queues do not use main thread at all. And the fourth point is that the priorities of these queues are decided by quality of services. Quality of services is something which decides the priority of these queues, because there are a number of system provided queues. So we can dispatch our job, we can dispatch our task on any of these queues, and then how those tasks will be executed, what will be the priority, that is something decided by QoS, and that we'll see in a minute. But before that, let's see the proof of third point, that concurrent queues do not use main thread in any of the possible scenarios. Let's jump to Xcode. Let's write a small piece of code here to understand that which thread is used by which queue. So I'll start with dispatch queue.main. Let's say async and we'll print something here. And there's a property called isMainThread through which we can check that the current thread of execution is main thread or not. So I'm using that in this print statement, that if thread is main thread, then print execution on main thread, otherwise execution on some other thread. This will be executing on dispatch queue.main, and we saw that main queue uses main thread. So our expectation is that the first statement here, that the execution is being done on main thread, should get printed. And now let's create one more, dispatch queue.global.async. So global is a way to access the system provided global concurrent queues. So here we'll use the same thing, but we'll change the print statement so that it's easy to differentiate. Execution on, let's say, global concurrent queue. Let's try and give it a run. We see here that in second case where we use the global concurrent queues, the output was execution on global concurrent queue. And that is because the check for which we use this ternary operator, that thread is main thread, that failed. And that's why the second statement got printed. While in the first case where we were using dispatch queue.main, that is, we were using the main queue and eventually the main thread, we got the output as execution on main thread. That is because this condition of thread.isMainThread was true. So this proves that the global concurrent queues does not use the main thread. And now let's discuss the point in which most of the developers get confused, that is user interactive quality of services. Don't worry if you don't know that what is quality of services or what is user interactive. We are going to see that in a minute, but just in case you know and if you get confused with that, so let's just try to use the quality of services here. Right, QoS, and let's just use user interactive. And now let's try executing this. Again, you see that execution on global concurrent queue. So even when I have used the quality of services as user interactive, it did not print execution on main thread, which proves that no matter what quality of services you are using or how you are trying to access the global concurrent queues, it is never going to get executed on main thread. There are some other advanced concepts relating to this which may change the output in certain cases, in certain scenarios, and that involves the concept of target queues and couple of other stuff. But that we'll see after understanding the target queues, which we'll be discussing later in this video. Now let's see that what is quality of service. We have been actually discussing it for past few minutes, that user interactive and how quality of service impacts the execution, the priority, and everything else. So let's see that what is actually quality of service and why it was brought, why it was introduced by Apple in the first place. Because whatever we have seen till now, everything was working fine. There was no need of quality of service. We have introduced this word in this video itself. So the concept of threading, multi-threading, time slicing, context switching, everything that we have seen till now, it was working perfectly fine. Then why Apple introduced this quality of service and what it is? So for understanding that, let's first see that how application is actually launched and what happens under the hood. Treat this as a sandbox of our application. Basically, everything related to our application will take place inside this box. When we tap on the app icon, system launches our application. Basically, it creates the main thread, and on the main thread, the application actually starts. The UI kit is tied to main thread, and then the app delegate is invoked. So all the necessary methods of app delegate, those are called, and then our application basically starts. We start receiving the events. The main thread basically waits for the events, waits for the user interaction so that the other parts of the application can be executed. The application can actually run the way it is supposed to be. Now imagine a scenario that your app delegate requires some data, requires some information from some database. So what you will do is that you will call the database, you will call necessary methods of the database to fetch the data from the DB, and that will be done from app delegate. Now till the time this process does not complete, your main thread will be involved in performing these actions, and hence it won't be in the state to listen for any of the events. So till the time this activity continues, if your user tries to tap anything on the screen, if they try to perform any of the actions, any of the user interaction, basically your app won't respond. So once you get the necessary data from the database, once you get the callbacks, after that the app delegate will update the UI using that data, and then again the main thread will be in a state to listen the events. Now if this happens in a fraction of a second, then user won't even notice, it will look fine, and even you won't notice as a developer, it will look that everything is good. But in case the database takes some time, maybe 2 to 4 seconds, 5 seconds or more than that in responding, then you will actually realize that your application has become unresponsive, And then for solving that, you will go towards multi-threading, and that's the way for it. That is why multi-threading exists. So what you will do is you will break this chain of calling the database directly from app delegate, and you will introduce one more queue that will be the user created queue or maybe the global concurrent queue, which will take care of making the necessary calls from database. That particular queue will get the callback from the database, while your main thread will be free for processing the events, for listening to the events. And once the data will be received from the database, then you will update the UI, and again the main thread will be free for the user interaction. So that way you have solved the problem of UI freeze, the unresponsiveness of application, and it's all good till now. Now let's see that where is the problem actually. So let's remove all of these for now, and let's just focus on these two threads. One is your main thread and one is the background thread created by the dispatch queue, the GCD. Now when you have two of them, and imagine that you have a single core. Although this is not the case these days, we have very advanced processors, quad core, hexa core, octa core. Basically they have so many cores in them for executing so many tasks in parallel. But just for the simplicity, for understanding the problem, imagine that the device on which your application is running, it is having one single core. Now on that one single core, you need to execute the tasks dispatched on these two threads, on these two queues, the main queue, the main thread, and the background thread on the GCD, the dispatch queue. How will that happen? So basically the question is that which one do we execute? Now your answer to this would be that we have read about the time slicing, the context switching, and everything that you told in the first video. That will come into the play, the preemption will happen, the task on the main queue, the first thread will be executed, then the preemption will happen, the context will switch on the second, the task on the GCD will be executed, again the preemption will happen, context will switch, and that's totally fine because that is what actually happens. But gone are the days when it was so easy to understand that just because of those two concepts, everything will be executed so smoothly. So for understanding the problem in a better way, involve some complexity. Think of the use cases where multitasking is happening. So yours is not the only application on the device. User is using your application in which you are having two threads and you are deciding on which one to be executed. At the same time, the user is using some other applications. Let's say they are listening to music, they are browsing on Safari, or maybe they are using YouTube or anything else that can possibly happen on the device. Now think of the processor. It is taking care of so many tasks, of so many processes. The context switching is happening across the threads of so many processes. The computation, the processing of so many tasks are happening at the same point in time. The processing is being done at such an extent that it will cause the processor to heat up. The heating will happen and eventually your other components of the device will be affected. To encounter this, we used to have a fan placed over the processor. So if you remember the CPUs, we used to have a fan installed over the motherboard and specifically over the part where the processor was placed. Even in the older laptops, you would have seen the fan. And the job of that fan was to balance the heat to keep the processor cool. Now in these days, the laptops that you are using, the iPads, they are so slim these days, the iPhones, the MacBooks, none of them are having that fan installed in them. Yet we are using so many applications, yet we are doing the heavy processings. So how it is being managed? And that is where quality of service comes into the play. So quality of service tells the system about how it should utilize the resources required for your job to be executed. You would be thinking how to utilize the resources, what I was referring to. So for any of your job to be executed, system requires various resources, as in it needs to decide that which thread it should be executed on. If it requires input output, the access to the iOS stream is needed, the timer coalescing, the scheduling priority for how long should your job be executed on that particular thread before the preemption happens. And there are certain other factors which should be set to a particular value so that the processor works optimally. Now because we cannot set these factors, we cannot change the values of each of these parameters depending on the job that we are dispatching on any of the threads. System has provided, basically iOS, the GCD has provided us something called quality of service, which is one single abstract parameter that will decide the values of all of these factors, all of these parameters, so that we can sit back and relax. All we need to do is just specify that which quality of service do we want for this particular job, and then everything else will be taken care by GCD. But essentially these four are the quality of services that should be used when we want to dispatch any of our tasks on any of the global concurrent queues. Let's see them. So first one is the user interactive. Now user interactive should be used when we are dealing with the animations. Basically any of the user interactive jobs, any of those kind of actions, For them, you should be user interactive. Now again, I am not saying that we should not be using the main queue. Main queue is the way. Main queue is the recommended way for dealing with the UI kit, for dealing with any of the user interactions. So then why user interactive quality of service has been provided? Now that is a very debatable point. If you'll go through the Apple forums, if you'll go through the Stack Overflow discussions, you will find many angles, you will find different approaches, different thought process behind using this particular quality of service, but that we will discuss in the video related to the interview questions and answers. For now, we can imagine, we can settle down on user interactive should be used when animations or any kind of user related job is to be done. The next comes user initiated. Now this should be used where we require immediate results. So for example, you are scrolling a table view, and for the next set of cells which are coming into the viewport, some data is required. So whenever any kind of data is required which will impact the rendering of the UI immediately, and that has been initiated by user, for those kind of tasks, user initiated should be used. Utility is something which is used for long running tasks. So you can think of maybe downloading something wherein user is aware of the progress. It is a long running task, but it is not something which is of that high priority that it is impacting the user experience at all. So in such scenarios, you can use utility. And background is something which is not visible to user at all. So for example, if you are creating the backups, or maybe if you are restoring something from the servers, maybe you can use background for that. If you still have some doubts about which service should be used when, you can ask certain questions to yourself, and then based on the answer, you can decide on which service should be used. So for user interactive, you can ask the question if updating of UI is involved. If the answer is yes, go for user interactive. For user initiated, you should be asking that is the data required for seamless user experience? And if the answer is yes, go for user initiated. The next question that you can ask is user aware of the progress? So for example, download. It is something which is not impacting the user experience, but again, the progress is visible to user. So for such kind of tasks, ask this question to yourself, and if the answer is yes, go for utility. And for the last, background, you should be asking that is user aware of the task? If user even knows if something is being done? And if the answer is no, go for background. Now comes the priority, that how system will allocate the resources for each of these services. So it goes in this decreasing order. The user interactive is having the most priority. Then comes the user initiated, then utility, and then the background. Apart from these four, there are two other QoS. One is default and one is unspecified. So default falls between user initiated and utility, while unspecified is something where QoS information is missing. The absence of QoS information is treated as unspecified, and priority wise it is least. Now let's jump to Xcode and see all these in action. Here's a code snippet. Just try to predict the output of this. Okay, let me walk you through the code. So we are having two dispatch queues over here. Basically, we are dispatching two jobs on these two queues. Both of them are using the global concurrent queues provided by the system, and we have specified the quality of service. So for the first one, we mentioned as background, and the job is being dispatched asynchronously. For the second one, the quality of service is user interactive, and this too is being dispatched asynchronously. If you want, you can pause the video for a while. You can give it a thought. You can try to predict the output. So let's try to work it out. For the first one, we are mentioning the global queue and the QoS as background. Okay, that is fine. I mean, we are using concurrent queue and we are dispatching as asynchronously. So remember what we discussed in the first video, that whenever we use async for dispatch, it means that do not stop the current execution, move to the next block of code. So cool, this will be dispatched on some other queue at some later point of time, or maybe separately, and then the system, the control will come to this point. Here also we are using a concurrent queue. Okay, and again this block of code, this for loop, is being dispatched to this particular queue of quality of service user interactive asynchronously. Cool. So by this we can say that we cannot predict the output, because the two codes will be executed on two different threads which we do not know about, and they will be executed asynchronously. So if two jobs are executing asynchronously on two different threads, it is not possible to predict the output exactly. But let's try to do something else here. Can we predict that which one will be finished first? Because both of these tasks will take almost same time. We are printing a number in the range provided, that is 11 to 21 and from 0 to 10. So both of these tasks are essentially same. Both of them are printing the numbers, and even the count of the numbers is same, that is 10. So let's try to predict that which one will finish first. Now from the discussion that we just had about the quality of service, we discussed that user interactive is having the highest priority, which means that even though both of these tasks will be executed asynchronously on two different threads, yet there are strong chances that this particular job will finish first because more resources will be allocated to this particular job because the quality of service is user interactive. So let's try and give it a run. You see that 10, that is the last element specified in this range, it got printed before 21. So even though numbers have been printed asynchronously, I mean they are not in the order. So after 0 we are having 11, we are having 12, yet we saw that 10 is definitely before 21. So can we say that this task which was dispatched on a queue using user interactive, it finished before the one which was dispatched on the queue using background as QoS. Now again, don't take me wrong, it depends on the complexity of the task. If you're downloading an image, if you're downloading a movie, then it's altogether a different matter. But we are comparing because both of these tasks will take almost same resources, almost same complexity. That is why we are trying to compare them. Let's run it one more time just to see if our assumption is right or not. Again, the execution of this block of code completed before the first one. Let's run it for a couple of more times just to see if our assumption is right or not. We see that every time the output is different, but 10 is definitely coming before 21. Let's try it one more time. Again, 10 is before 21. So this shows that when we go for user interactive as the quality of services, it gets more resources, it gets more priority basically. So that was about quality of service. We will see more code snippets related to the serial queue, concurrent queue, synchronous, asynchronous, and those kind of executions. But before that, let's have a look at the custom queues, the user created queues. So let's see that how custom queues can be created and what are the parameters that initializer takes. So this will be a dispatch queue, and in the dispatch queue, we see that these are the parameters. So label is one, then QoS, attributes, auto release frequency, and target. Okay, let's try to understand them all. Label is basically the name of the queue. It is an identifier provided at the time of initialization and can be used later for the debugging purposes when crash happens, when you want to check that which particular queue was in action at this point of time. You can use this label so that you get the name of the queue and then you can debug accordingly. So that is about label. QoS we saw in detail, what are the quality of services and everything. Now let's see what are attributes. So attribute parameter can basically take three values, either concurrent or initially inactive or both of them. Now what does they mean? Concurrent is basically used for creating any concurrent queue. So by default the queues are serial in nature. If you want to create any concurrent queue, you can specify the attribute as concurrent and then the queue that you will get, it will be a concurrent queue. Initially inactive attribute is used when you want the execution of that queue, whatever the task has been dispatched to that particular queue, when you want that their execution should start at later point of time, not immediately as soon as you dispatch the task. For those scenarios, you can use initially active. And later when you want to start the execution of those tasks dispatched on that queue, you can call the method activate on the object of dispatch queue and the execution will start. You can use both of them if you want a concurrent queue that should be initially inactive. So you can pass both of them in an array and then you will get a concurrent queue which is initially inactive. So that is about attributes. That was quite easy to understand. Now the next thing is target queue. So there was one more parameter, if you would have noticed, that was auto release frequency. We will come to it later. I mean, we'll come to it after understanding the concept of target queues, because auto release frequency somewhere requires the knowledge of target queues. So let's understand that what is target queue, and this is a little advanced topic I feel, because in interviews whenever I have asked candidates about target queues, I felt that they struggled a little bit. So let's try to understand this in detail. So target queue is basically a queue on which the actual execution happens. So when you create a custom queue, you might think that whatever task, whatever job that you will be dispatching to this queue, it will be executed on this one. But behind the scenes, they are actually executed on some other queue, and that is the target queue. So system has a fixed set of queues And all the jobs that you dispatch on either the global concurrent queues or your custom created queues, they are executed on those fixed set of queues which are the target queues. Now you can definitely change the target queue of your custom queues if you want to change the behavior of you, or if you want to play with the system. So that provision is always there. You can change the target queues, but essentially the point to understand here is that whatever task that you dispatch on your custom queues, it is actually executed somewhere else, and that queue is known as target queue. Now comes the point that what about the priority? Because for last 10 to 15 minutes we have been discussing about the quality of service, the priority, and those kind of things. So if we say that our job will be executed on some other queue that will be the target queue, what will be the priority? So any queue that you create, its priority will be inherited from the queue on which the actual execution will take place, that is its target queue. Okay, so the next question arises that what if we do not specify any priority? Well, in that case the default priority would be the default priority global queue. So we saw that there were 4 quality of services and then there were 2 more, the default and the unspecified. So in this case, the default priority global queue would be used as the priority of your custom queue if you do not specify any of the QoS for your queues. You would be definitely thinking that why the concept of target queue exists at all. So the thing is that if system would have provided the freedom and flexibility of creating as many queues as you want, the developers would have definitely messed up with the resources of the system, and to keep them in control, there are definite amount of queues on which the task is actually executed, but you can always create the custom queues for your own flexibility for managing the things your way. Cool. So after understanding this, the obvious question comes that where can we use target queues? What is the actual use of them? And as the proper answer to this question, I would say that with experience you learn how to use the target queues, and as the shorter explanation or one of the easy use cases of target queue is this. So here you see that we have 2 queues A and B, and assume that both A and B are serial queues. So when I say that they are serial queues, it means that one task will be executed at one point of time. Task 1 will be executed and then task 2 will be executed. Similarly on B, 3 will be executed and then 4 will be executed. So both of them are serially independently. What I mean is 3 can execute after 1, or maybe 3 can be executed at the same time when 1 is being executed, because the execution is being done on a different queue. Although 3 and 4 will be executed serially because both of them are on the same queue, that is queue B, and 1 and 2 will be executed serially because they are on a different queue. But what if we want all the 4 tasks to be executed serially? So basically what I mean is that I want to make both the queues A and B serial to each other. In that case, we can introduce a queue T, which will be a serial queue and which will be set as the target queue of both A and B. So whatever tasks that are dispatched on A or B, they will be eventually executed on T, and because T is a serial queue, it makes both A and B serial to each other. So the task will execute this way: 1, 2, 3 and then 4. If we talk about other use cases, target queue can also be used for changing the priority of the task. So let's say if you are having a custom queue and if you want the jobs dispatched to this queue to be executed on a lower priority, you can set the target queue as background or maybe utility, or if you want them to be executed on a higher priority, you can change them to the user initiated. So that way you can change the priority using target queue. That is also one of the use cases. But for better understanding, let's jump to Xcode and let's see target queue in action. So I have a code snippet here. Let me walk you through it first and then you can try to predict the output. So we have a queue A, which is labeled as A, and because anything has not been specified explicitly, so by default this A is a serial queue, because unless we specify attribute as concurrent, it is a serial queue. Then we have a queue B labeled as B, and we specified that this is a concurrent queue. We also specified that this targets to queue A. So any dispatch queue can target to any other dispatch queue. Just make sure that you do not create the cyclic dependency. But other than that, you can always target to any of the queues. So this dispatch queue B is targeting to the serial queue A. Now on queue A, we are dispatching this block asynchronously, that is printing of numbers from 0 to 5. There's another block being dispatched asynchronously, which involves printing of number from 6 to 10. There are other 2 blocks of codes which are being dispatched to queue B asynchronously. And note that we explicitly mentioned that B is a concurrent queue. So on this concurrent queue B, we are dispatching this block of code to be executed asynchronously, and this one too. Now you can try to predict the output. You can pause the video for a while and give it a thought. So let's try to work out the easy part first. A.async. A was a serial queue and this block has been processed asynchronously. So we will move on to the next block of code, which is this block of code. But because A was a serial queue, so one will be executed at one point of time and then the execution of the next block will be started. So this will print 0, 1, 2, 3, 4, 5. Then the next set that was in queue, that was 6, 7, 8, 9, 10. Then on B, we have dispatched this as asynchronously and this too. And it appears that B was a concurrent queue. So both of these will be executed parallelly and asynchronously, of course. But the point to notice here is that the target of B was set as A. And we discussed that when we specify a target queue, the behavior of that target queue is inherited. So because A was a serial queue, now B will also act as serial queue, because whatever that has been dispatched to B, that will be actually executed on A, which was a serial queue. So these two blocks will also be executed on a serial queue asynchronous. Well, asynchronously doesn't matter here because the next block of code will be again dispatched on the same queue, and then because it is a serial queue, it will be processed one at a time. So in that case, the output for these two blocks will be 11 to 15 and then 16 to 20. Now let's give it a run. And we see that the output is 0 to 5, then 6 to 10, 11 to 15 and 16 to 20. So basically all these four blocks were executed in a serial manner, though B was a concurrent queue because the target was set as A, which was a serial queue. So that is how we can use target queues. One of the things to remember about target queue here is that if you do not set the target at the time of initialization, you cannot change it later. Although we have a method named setTarget for changing the target, but if we try to execute that method on an already activated queue, it will result in a crash. So let's try for that. Let's say we have B here, and let's not specify the target at this point of time, but after the initialization, let's try to change the target b.setTarget as A. Now if we try and running this, we'll get a runtime error because we cannot change the target of an already activated queue. If we do not want to set the target at the time of initialization but want to change it later, in that case the queue should not be activated. So for that we can use the initially inactive attribute and then can change the target later. So let's try doing that. Let's mention the attribute as, okay, concurrent was there, and along with that let's mention initially inactive. Now because this queue is not activated yet, we can change the target, and after this point of time we can say that b.activate. So this queue B will be activated after the execution of this line, and before that we can change the target. So now let's try and give it a run. Or maybe to understand, let's dispatch something on B. So b.async print testing activation deactivation, let's say, and let's try and running this right there. So we see that the crash, the runtime error that we encountered earlier, it did not happen this time, and that is because we changed the target while the queue was not active. So this is something that we should keep in mind while changing the targets or while thinking of target queues. Now the last parameter remaining is auto release frequency. Let's have a look at that. So auto release frequency is basically a constant which tells about the frequency with which dispatch queue auto releases the objects. So I'm expecting that you know about ARC and that it takes care of the memory management, the auto release of the resources of the objects. So auto release frequency is related to that only. It tells about the frequency with which the dispatch queue auto releases the objects, how the auto release pool is managed by the dispatch queues. So essentially we get three options here: the inherit, work item and never. In case of inherit, the behavior is inherited from the target queue, and that is why we understood the target queue first. So in case of inherit, whatever the auto release behavior is there with the target queue, that will be inherited in case of inherit. Now when we specify it as work item, it means that an individual auto release pool will be set up for that particular dispatch queue, that will be pushed while the execution will start, and that will be popped when the execution will complete. That is in very layman terms, but it should be treated as an individual auto release pool is set up in case of work item. And in case of never, a different auto release pool is never set up for that particular dispatch queue. I'll focus more on this when we'll discuss the memory management, the ARC stuff and those kind of things. But for now, it's good to understand that there are three options available for the auto release frequency, which tells about the frequency with which the dispatch queue will auto release the resources which is being used for the jobs that are dispatched on those dispatch queues. Now, before summing up this video, let's jump back to Xcode and work out some other code snippets which will give us some insights about the behavior of dispatch queues. Now, this is going to be very interesting. So I have some saved code snippets here, and I have taken these code snippets from the articles by Aina Jain. If you want to follow those articles, I'll mention the link in the description. Do try to read them, do try to follow them. She has covered concurrency in a very detailed and in a very good manner. So these are the references from those articles. And because you already covered those concepts in these examples, I'm not reinventing the wheel by writing the same code for the same thing. Let's try to understand those examples. So let's go with the serial queue async one first. Let's see that what is actually happening in the code, and then we'll try to predict the output. So this is our method do async task in serial queue, and before that we have our serial queue declared over here. And this is actually the good practice. So for giving the labels, we should always use the reverse domain. So com.queue.serial. Okay, we have a serial queue here which is being used inside this method. So let's not go through this first. We'll go through this when we'll be calling this method, when we'll be executing this. So this is the call for this method. Now let's see over here, we have a loop iterating from 1 to 3. Inside that we are dispatching this particular block asynchronously on a serial queue. Again, when we dispatch something asynchronously, it does not block the current execution and moves to the next line, next piece of code available for execution. So let's leave it here for now. And the next line that we see that is to be executed is that we are dispatching another block of code on the same serial queue. So these two blocks will be executed serially, and this was also dispatched in an asynchronous manner. So this line will be executed, that is last line in playground. Okay, let's hit the play button and check the output, and then we'll try understanding it. So we have got task running in other thread. Okay, so for understanding this, let's go through this method, what is happening over here. So the block that we are dispatching asynchronously on the serial queue, in that we are having the check for the thread on which the execution is happening. If it is a main thread, if it is happening on main thread, task running in main thread will be printed, otherwise the other thread will be printed. So this dispatch queue, this is our custom queue, and we saw that any global queue or custom queue, they do not use main thread. So that is why task running in other thread has been printed over here. There's a concept related to this which we will see in a minute, but for now let's just stick to our basics, our concepts, that main thread should not be used. Main thread is not used by any of the custom created queues or the global concurrent queues. So that's the reason we got running another thread here. And now we are actually downloading an image, so this will take some time, and then we'll see the counter variable over here, the one finished downloading. Meanwhile, because this was being dispatched asynchronously, so this will be executed on a different thread. So meanwhile, this last line in playground that got executed because control proceeded from here. So that is for last line in playground, then one finished downloading, again task running in the other thread for the second iteration, then again two finished downloading, task running in other thread, three finished downloading. So because this block of code was executed 3 times because of the loop, that is how it ran. And because this was a serial queue 0 1 2 3, the next block of code that is printing of this value with this star sign, that got executed after the completion of this block. So this justifies the output. So whatever we understood about the dispatch queues, we can actually use our knowledge to predict this output, and we can justify this output. What are the reasons for each of the print statements? So this was the example of something being executed on a serial queue in an asynchronous manner. Now let's move on to the next set of code, which is serial queue in the synchronous fashion. This is almost same as the previous one, but the difference is that here we are using sync for this block of code, while async is still here for this one. Now this will change a lot of things. I suggest you to pause the video, think of the output, and then check that what actually happened. So let's hit the play button and let's try to see the output. the first line in the output itself, that is task running in main thread. This challenges our entire understanding that we have developed over the time. So we discussed that main thread is used by main queue only, and the other queues, they do not use the main thread, they use some other background thread. So in this case, this was a custom queue, dispatch queue, and this should have used the other background thread. And if that was the case, then this if condition should not have been executed, and eventually the task running in main thread should not have been printed. So what went wrong here? What happened differently? So as a justification to this output, when we use sync block, basically when we try to synchronously dispatch some block of code, some piece of work to any dispatch queue, and if that dispatch try to block the main thread, so whatever execution that was happening on the main thread, if that is not continued because of that sync block, then system may or may not use the main thread for the execution of the task that you have just dispatched to some queue. Let's try to understand it slowly. So whenever you use sync block with GCD, and if for some reason it hinders the execution of the main thread, so whatever that was being executed on the main thread, if it is stopped because of your sync block, and now that the main thread is idle, system thinks that why not this block of code should be dispatched on main thread itself, because anyway main thread is idle because of the sync block. So in those cases, system tries to utilize the main thread. Now this is a concept which is very contradictory, which is very conflicting with all the definitions and all the standard descriptions about the APIs which has been provided by Apple. But again, it is important to understand that it may or may not. Now because this is being executed in the playground where we don't have anything else, there are no threads created, there are no background processes working. So this can change in an actual project. But for this scenario where we have nothing else, we have actually blocked the execution that was happening on the main thread. And because system found that main thread is idle, let's dispatch this job on main thread itself. And that is the reason we saw this line in the output, that task running in main thread. So this justifies, and then the other outputs are pretty easy to understand. So one finished downloading, so whenever that downloading of the image completes, one finished downloading will be printed. Task running in main thread, we just went through the justification of this statement, then to finish downloading, that is how it went. And then the next block was dispatched asynchronously, so the execution of this line happened, which is last line in playground, and then 0 1 2 3 as expected. So that was about the serial queue with synchronous block. Let's move to the third, that is concurrent queue asynchronously. The same code, the only difference is that we have introduced the attribute here, and we have explicitly mentioned that this is a concurrent queue. Concurrent queue, this block of code is being dispatched asynchronously. Let's try to look at the output. Now because the queue was concurrent, multiple tasks were executed at the same point of time, and this justifies that task running in other thread. Again, this block was dispatched asynchronously. Because it was dispatched asynchronously, it did not block the execution that was happening on main thread. The main thread is not idle, it is working on something else, and hence the task running in other thread got printed, again as a justification to the previous output. So task running in other thread, this was asynchronous. Then last line in playground, this was also dispatched asynchronously on a concurrent queue. So it started after the execution of the first one, but we cannot guarantee that when which task will be finished in a concurrent queue. Hence 0 1 2 3 got printed, and then the other output 2 3 1 because it is a concurrent queue, and the job has been dispatched asynchronously. So this justifies. And now the last piece of code, which is concurrent queue in a synchronous fashion. The same story again. The only difference is that now on this concurrent queue, this block of code is being dispatched synchronously. You are thinking it right. Task running in main thread. This is what I meant when I say that you are thinking it right. So this was in playground, we used synchronous dispatch on a queue. This blocked the execution of the main thread. Main thread was idle. System thought of dispatching this particular block on the main thread. Hence we got task running in main thread. And then the other output is pretty easy to understand. It's 1 finished downloading, task running in main thread, 1 2 3, because this 1 2 3 was dispatched asynchronously. So before execution of this one, control jumped to the next line, which was last line in playground. So that's why this got printed before this one, and then 1 2 3. So this justifies the output. Now this was a very interesting concept to understand, that at times it may appear that your job will be executed on some background thread while it can actually take place on a main thread. But this is again subject to many factors, many conditions, and it may or may not. System takes care of that. But it is important to understand this. That's pretty much for this second video in the series of mastering concurrency in iOS. In the next video, we will try to understand dispatch in even more detail. We will see dispatch work item, dispatch semaphores, dispatch group, barriers, logs, those kind of stuff. Next video will be available very soon, and if you like my content, if you like my videos, you can consider subscribing to the channel. Till then, take good care of yourself, happy coding and stay safe.